Our focus this time is going to be on those curvy graphs that we saw in the previous part of the lesson. So the exponential graphs, they are called because, again, the variable is in the exponent. Now, they come in two types. So we saw one type that curved up. We saw one type that curved down and flattened out. Those are the two types. Which type is which depends on what the value of b is in this equation. So this is one I need you to recognize and know. This is what exponential graphs look like. A number times another number to the x power. Now in these four examples, there's four of them there, the a number is just 1. And because multiplying by 1 doesn't change anything, that's why there's nothing written there. We're going to be looking at these graphs just to see the different types of exponential curves you can get. All right, do this for me. If you haven't already pulled up a Desmos graphing calculator, get one ready because we're going to graph these and look at them. So I've got a nice blank Desmos. Let's see what we can do. The first one we're going to examine is y equals 1/3 to the x power. The parentheses matter. If you've got a fraction to that power of x, if you don't have the parentheses in, it is not going to do what you want. So 1/3. And then for the exponent, I just pressed Shift 6. You can also use the calculator at the bottom to get the exponent there. There we go. That's what this graph looks like. Notice that as you look at it left to right, so like you're reading a book, it goes down. We're going to bear that in mind. Okay, let's turn that off temporarily and look now at our next one. F of x equals 1.5 to the power of x. Okay, so coming here to Desmos, f of x equals. Now, when it's not a fraction, the parentheses aren't as important. Put them in anyway. I would much rather have you have them there. That way you don't forget them when you do need them. Okay, notice this time the graph goes up. So in our previous one, as you looked at it left to right, graph came down and leveled off. This time, as you look at it left to right, the graph starts low, leveled off, and then goes up. These are the two types of graphs that we're going to see. Now, did you notice how the first one was y equals and the second one was f of x equals? It makes no difference. They are the same thing. So when you see either notation, it doesn't change what the graph is. So I'll use those interchangeably. On your practice, you may see those used interchangeably as well. Okay, let's keep going here. We got two more to look at. F of x equals 4 to the x. Ooh, you see that time I left out the parentheses? Not a bad idea to always have them. So this is another one of those types that goes up. So it starts flat and then starts curving up real quick. And then our last one, y equals 0.6 to the power of x. 6 to the power of x. Again, going to put some parentheses in just so I remember to do that each time. And this is another one of those that tends to go down. So it starts high and then comes down and flattens out. So these two follow that pattern, the starting high and then coming down and going flat pattern. These other two follow the other direction. They start low and flat and then grow high as you move to the right. These have names. We call these exponential growth and exponential decay. Exponential growth is the one that goes up. So it starts low and flat and then goes up like this. Exponential decay is the exact same thing flipped around. So it starts super high, comes down, and goes low and flat. Ooh, I'm going to try that one again. I'm actually going to, I think, draw it in the other direction. There we go. That's a little better. Yes, I do need you to know that the first is called exponential growth because it grows. This one's called exponential decay. Decay meaning it goes down and gets smaller as you go. How can you tell which is which if you don't have the picture in front of you? It's very simple. You look at these numbers. you look at the numbers that have the x as the exponent. Turns out, what did we see? This one and this one ended up being exponential decay. Well, 1/3, that's a pretty small number. 0.6, that's a pretty small number. Specifically, it's a number that is between 0 and 1. If you put a number between 0 and 1 as what we call the base of your exponential, you're going to get exponential decay. On the other hand, we had exponential growth here and here. 1.5 and 4, those are both bigger than 1. That's what makes exponential growth happen. So let me summarize it here with some words. So exponential graphs, both of these that we looked at are exponential graphs. They have a domain of all real numbers, meaning the graph goes to the left forever and goes to the right forever. Since an exponent can be any number, the variable this time, the x, is the exponent. We can deal with positive exponents. We can deal with an exponent of 0. We can deal with negative exponents. Remember, that just gives you fractions. It flips things upside down. Exponential graphs have what's called a horizontal asymptote at y equals 0. Let's come back here. All of these, if I graph in now the line y equals 0, I'm going to make it easier to see. Let's make it orange and dashed. All of these graphs come down and go flat at this line y equals 0. And it's because of what we talked about in our previous discussion. Because your negative exponents give you very, very small fractions, you get outputs. You get y values that are very, very, very close to 0. But they don't ever actually get all the way there. That's what an asymptote is. A line that you get very close to, but don't ever actually touch. And the reason, when you take a positive number to any power, you end up with a positive result. It could be very tiny, it could be very big, but it's always going to be some positive number. And it's for that reason that the range of our exponential graphs is always y greater than 0. So I would summarize it like this. Domain-wise, this is describing what your x's can be. So x may be any real number. Positive, negative, 0 doesn't make a difference. But range, this is describing your y's, positive outputs only. As we take a look at these graphs here, notice that all the y coordinates, so look at the second coordinates in the ordered pair, they're all positive numbers. There's nothing down here. There's no graph down where the y's are negative, and it's because of this exponential relationship. Very special relationship. All right, so what do A and B actually do? To determine that, we're going to go back to the Desmos. I hope you've got that open. I'm going to turn these off and put in now y equals a times b to the power of x. And when you do this on yours, it's going to say, hey, do you want to add sliders? I want you to choose all. And when you do, you're going to get a graph that doesn't look very interesting. What I want you to do is change the boundaries on your sliders. So click here under the A where it says -10. Would you just make your range of A go from 0 to 10? So 0 on the low end, 10 on the high end, and then just click out of the box. You'll notice your range now goes from 0 to 10. For your B, I'd like you to do something similar. Let's have this go just from 0 to 5. For your B's, click on there, change 0 to 5. And now I want you to take a little time and just move those sliders around. So do a pause here, move your sliders, see what happens. And then when you're ready, come back, we'll continue the discussion. Giving things a look here. Okay. So first off, I do want you to make sure you noticed that when your B is any number bigger than 1, you've got that exponential growth graph happening. But if you make your b small enough, meaning less than 1, now you've got that exponential decay happening. So b determines whether you have decay or growth, decay or growth. Did you figure out what a does? A is 2.8, the y-intercept is 2.8. A is 4.4, the y-intercept is 4.4. Doesn't even matter if you have growth or decay. If A is 1.8, my y-intercept is going to be 1.8. So coming back here, let's summarize this up. What is A? A tells you what your y-intercept is. The B, I hope you saw, determines how much your graph curves. We're going to call that the rate of change. Very, very large B gives you very quick growth. Very, very small b gives you very quick decay. And any number close to 1, like a 0.9 or a 1.1, gives you slower growth and slower decay. Let's wrap up this discussion this way. I'd like you to understand why A gives you the x-intercept, or the y-intercept. For that, I need us to think about what it means to be on the y-axis. Any point on the y-axis is going to have an x-coordinate of 0. Every time, all the time. So I'm going to be putting 0 in for this x. We've discussed a couple of times in this lesson already. Any number to the 0 power is always equal to 1. And a times 1 is just a. It is for that reason that the a in this equation ends up determining what your y-intercept is. So, hey, play around a little more. The more time you spend becoming familiar with how these exponential graphs look, the easier it's going to be for you to use, interpret, and understand these graphs as well.